where y is discrete. Okay, so this could be a Bernoulli, or a multinomial. I'm not really allowing other formulations. And this is a real value, which means logistic regression, even though it's a regression, it's really a classification problem. You're not really solving regression. The way we treat it.
Well, does regression just innately have a distance function associated with it, whereas the...
It has some link function. So you have some loss. So the loss is logistic in one case. It's squared error and linear. So they're both regression. But when I'm saying regression here, I mean f of x maps to a real value. So you're looking at the raw value. It is true, logistic regression, you're getting an interval between 0 and 1.
Yeah.
But we're using it as a classification model. It's subtle, but just whatever. I won't be quizzing esoteric about that. How to model x. So you should have some idea of how to make features. So like bag of words was one feature model that we did. For like weather problems and all this kind of stuff, we modeled positional base that specifically the question was asked like, is X1 sunny? You know, it's not just is the word contained in the document. Like there's not always exchangeability. Sometimes there is. The problem I gave in the lecture was we did context sensitive spelling. So the X's were is the word before blah, right? You have a feature vector for that. Something like this. But you could have features for anything like the sentence. I don't expect, I'm not going to ask you to model, but you should have some idea of how to convert. If I was to ask a problem like, I want to predict the weather, tell me how to set it up. You should say, define the weather as some set of classes, that's your y, there's some features, something like that. Okay. Quick interval, just K-nearest neighbor. Nothing fancy about it, but be aware it exists and what it does. Decision trees. The big things to know here is, it represents a DNF, or it can represent lots of logical forms. So like complete logical form. And we use ID3 to learn trees, which is the information game. And actually, the practice question is fairly representative of what I would expect. I think that would be a fair question if there weren't typos in it for the midterm. So it's about the right level. Okay. Probabilistic modeling. So you should know joint probability, distribution. You should know generative modeling, or generative models. In this case, of course, the ones we know best are naive Bayes and Gaussian naive Bayes. And the distinction here, again, this has to do with modeling your x. If you have discrete variables for x, you use something more like naive Bayes. If you have real values for x, you need to somehow model with some continuous distribution. Okay. Parameter estimation. This is basically maximum likelihood and map. Yeah, and we'll say some more about that today. And then a little side note, EM is a specific kind of parameter estimation when you have missing variables. Okay, you have conditional models. And And so the distinction here, by the way, in a generative model, you're modeling P of x, y. So you're modeling the joint. Here, you're directly modeling P of y given x. Parameter estimation here. It's still map and MLE, but we also want to know about gradient descent, so GD, SGD. And finally, I say regression modeling, but really I just mean linear. And we're not interested, I'm not wholly responsible for closed form like matrix operations. If you've seen it in another setting, you've probably seen it for, x transpose x inverse times y, that kind of stuff. I don't expect, there will not be any kind of matrix operations because I've avoided matrices kind of wholesale, because we've never really done kind of like multivariate Gaussian things that really require, there's vectors but not matrices. Okay. Now, I can just cruise through. Oh, maybe that'll work. I don't know if I like this. Yeah, this can mostly be skipped, but yeah, okay. So nobody cares. Let's see. So in this case, this is what I'm just saying about being able to kind of know, this is what machine learning does, and then one step would be how to model the individual games or individual whatever you care about. I want to actually get to the second lecture. This is not super exciting. Maybe I should bring it up. Well,
should we be expecting any interpret questions?
What do you mean?
Here's some model, some result, or your probability matrix, or whatever. Interpret the result.
If I was to, I'm looking. Yeah, those tend to be kind of fishing, so I don't avoid. I try not to make it too open-ended, like I did on the homework, where I'm more interested in actually thinking about it for a while. But I might ask, I might be looking for a specific statement about like the size of trees or something like that, like it's on,
like in practice.
Like on the practice exam, basically. So context-sensitive spelling was an example I said earlier. Oh, sorry, wrong lecture. Let me get that in the second one. I should have skipped through it immediately. Okay. So this is where it's more relevant. Okay, so everyone, I hope is familiar with the we go to it. There's decision boundaries. They're a little more complicated when k gets greater than some value. This is our setup here. It's just as I said in the outline. We're going to get some set of training examples, learn some function that maps any x to any y. Y is classification, y is regression. And x is something we don't really talk about in this class. We kind of limit ourselves to machine learning methods, but it's important to know how to specify feature vectors. And I've said it enough times now that I think it's clear I'm asking something about features at some point. So if I wasn't clear from the hints, so features describe instances. These are kind of different types of features. You've seen all of them, I think, at some point, either in a homework written problem or coding problem. Okay, this is boring. I guess actually, let me just pause. So these kind of questions, like you may not have gotten it the first time through. Now that you're looking at it again, does it kind of make sense? What I was getting at here, the idea that bigger hypothesis spaces require more data to learn effectively. If you have a smaller space, your results are more likely to generalize. These are kind of easy things that are good for short questions. So. Yeah. Let's see. So you've seen this a couple times now. This is a good general form. You saw on the practice midterm I asked about gradient descent in the broad case. I think that that's kind of fair. By now you've been introduced to map and regularization generically. So you should have some idea that what we're doing here is minimizing some loss and have some regularizer that we think will do well on our testing data. In this case, for context-sensitive spelling, the function we're learning is some classification task into some confusion set for a given word. In our representation, the vectors here would be things like the word before, the word two words before, stuff like this. So, you've seen this again by now. It's fairly straightforward, different losses. We've only talked about squared loss and logistic loss for problems. LMS, this is code actually for linear regression. LMS is stochastic gradient descent for linear regression. So you were briefly introduced to it before you actually had any reason to know it directly. What you see here, that my parameters is my weight vector here. And basically all I'm doing is just updating my weight vector for every example such that it's a learning rate minus the error. This is just SGP, effectively. And I call it here, obviously. Generalization, that doing better on training doesn't necessarily mean you'll do better on testing. There's some idea that as you're training here, there's some sweet spot where they're both kind of pulling data from the same distribution, and if you have a training algorithm that fits the corners of your training data, it may very well be that it'll do worse on testing data, which is why we have the regularization. But that's why we do lots of things like, we don't want trees to be super deep because it overfits the corners of the space. This is a really important concept. To be honest, I'm eventually later going to do the bias variance trade-off, and that's where this comes up much more explicitly and rigorously. But just, it's a good thing to know. Yeah. So, while this is like the easiest lecture, obviously, are there any questions about any of the concepts on it?